Before we do the real work in this video, I want to start with a quick review. Let's recall what it means to multiply a matrix times another matrix. And in this case, I'm calling this a matrix. It's really a column matrix. A vector is really just a column matrix. Or if you choose to write it in the format 1, 3 or 1, 3, then we could call that a row matrix. But just for the sake of argument, I'm talking about these as though they are matrices for the purpose of actually multiplying them together. So what does this multiplication look like? Let's take A, which is -4, 2, 0, -3, and multiply it on the right by the vector 1, 3, or the column matrix 1, 3. Now, first of all, let's remember that we can do this because we know this is a 2 by 2 matrix and this is a 2 by 1 matrix. If these two numbers match, we'll be able to do this multiplication. These two numbers tell us the result of the dimensions of the result. So we know when we do this multiplication, we're going to end up with another 2 by 1 matrix or a column vector. Okay, so what does that look like? Well, I'm going to multiply row 1 by column 1. That's my only column, but that's okay. Let's get rid of this. Row 1 times column 1 is -4 times 1 plus 2 times 3. And then I'm going to take row 2 and multiply it by column 1. That gives me 0 plus -9. And if I simplify that, I get 2, -9. So that is how we do matrix multiplication. And in particular, one of my matrices here is a column matrix, otherwise known as a vector. So I was able to do this matrix multiplication, and when I did, I got this result. Now, sometimes this vector here, when we do this multiplication, if the vector is just the right vector, it produces a very interesting result. Let's take a look at A again, but in this time, let's multiply it not by the vector v that we have here, but by the vector 1, 0. That's going to give me this multiplication, which looks like -4, 2, 0, -3 times 1, 0. That will give me -4 times 1 plus 2 times 0. And 0 plus 0. Now, if I scale this vector back as much as I can, in other words, if I factor out any common factors here, I get something that looks like this. And what we want to notice here is that this vector is the same as this vector. And so we're going to call this vector an eigenvector. It's a vector which, when you multiply it by this matrix, gives you, as a result, the exact same vector as you just used to multiply it with, but scaled. It's a scalar multiple of the vector you originally multiplied by. I'm going to rename this vector x1 because it turns out eigenvectors are not necessarily unique. Let's see what happens if we multiply this same matrix A by the vector 1, 1/2. I'm going to get 4 times 1, -4 times 1, that's -4, plus 2 times 1/2, that's 1. -4 plus 1 is -3. And then I'll get 0 times 1, which is 0, plus -3 times 1/2, that's -3/2. And I see a -3 in both of those, so I'll pull that out to the front, and I get 1, 1/2. That means that this vector is an eigenvector because this vector is a scalar multiple of that vector. Over here I see, I did it slightly differently in the green example than I'm doing it in the pink example. I have the resulting vector unscaled, as it were, with a factor pulled out. That comes, though, from this vector here. So this vector is the result of the multiplication, but the vector we multiplied with, because when the multiplication is finished, we have a scalar multiple of that vector. This vector here is the same as this vector here. This vector here is the same as this vector here with the -3 pulled out. When you have that result, we call that an eigenvector. So I've used the same matrix A with two different vectors, and I've gotten the same result. Not the same numerical result, but the same. Let me use a highlighter here as well. What did I do? Green. Okay. This vector is a scalar multiple of this vector. This vector is a scalar multiple of this vector. These are different vectors. Here I multiplied by the vector 1, 0. Here I multiplied by the vector 1, 1/2. The result is a scalar multiple of the vector I multiplied by in both cases. These are very different vectors, but the vector I used to multiply by is called an eigenvector because the resulting vector is a scalar multiple of that vector. It's worth noting that if I had a different matrix here, these vectors would not work necessarily, quite likely. I mean, there's an infinite number of real numbers, so there are an infinite number of matrices made up of real numbers. So an infinite number of vectors, infinite number of matrices I can use here, and an infinite number of vectors I can use here, but the particular combination of a matrix times a column matrix or a vector, which produces a scalar multiple of that vector, the vector you used for multiplication is called an eigenvector. The notation we're going to use here is to say that if I take a matrix A and multiply it by a vector, and the result is just a scalar multiple of that vector, I'll call it, I'll call it, I don't know, B for now. B is just a number, right? It's a scalar. If that's true, if you can make this true for some real number B, this is just a real number, this is a vector, this is a matrix. This is a weird equation. This looks like a matrix. Matrix multiplication produces a matrix, is a scalar multiple of a matrix. And that's exactly what we're saying. If that's true, then we're saying that x, that vector, is called an eigenvector. And we're also going to use a little different notation here. Instead of using a number B, we're going to use, this is just a convention, but get used to it because this is what you'll see. We're going to use this weird looking thing here. It's the Greek letter lambda. If you didn't have enough Greek letters in your life already, here's another one, lambda, and that's spelled Lambda, which is weird because we don't, how do you spell the letter A? Right? This is just a Greek letter. So, but for pronunciation purposes, we spell it. We spell the pronunciation lambda, and this is what the Greek letter looks like. Okay, so this is what we're after here. What is an eigenvector? It's a vector which, when you multiply it on the right by a matrix and a scalar, the result is the same. In other words, the result of multiplying this matrix on the right by this vector is just a scalar multiple of this vector. And when you do that, the vector you've used in both cases is called an eigenvector. Lambda is called an eigenvalue. It's the value, it's the scalar, right? So if I go up here, -4 is my eigenvalue. 1, 0 is my eigenvector. Here, -3 is my eigenvalue, and 1, 1/2 is my eigenvector. And so you'll notice that I have a scale paired with a vector, a scale paired with a vector, and oftentimes you'll see that that scalar, lambda, the eigenvalue, and the eigenvector, x, we call that an eigenpair. just for some more vocabulary for you. This is an eigenpair. This scalar only works with this vector, and this scalar only works with this vector, and this vector only works with this scalar to give us this result. So these things are paired in the same way that if you want to get to a point on an xy plane, you have to go x comma y, and only x comma y, only that combination of over and up will get you to that location using Cartesian coordinates, right? So we can pair these because they are unique in their combination. When I use the vector 1, 0 with this particular matrix, the scalar is going to be -4. It's never going to be anything else. When I use this vector, the scalar is only going to be -3. It's never going to be anything else. So that particular pair is unique, and that particular pair is unique. And as such, we sometimes write them as pairs. So for example, my two answers here would be -4 and x1, and -3 with x2. Anytime you multiply a matrix by a vector, right, we're going to get a vector. Where did this one go? Oh, here it is here. But this 2, 9 is, let's see, 1, 3 is here, and 2, -9 is down here somewhere. So not to scale. Now, these vectors clearly do not go in the same direction. I mean, it's just matrix multiplication. A matrix times a column matrix gives you a new column matrix, a vector. So I'm multiplying this matrix by this vector to get this vector. There's the vector I multiplied by, there's the result, right? But if I multiply this matrix by this vector, let's throw this vector in, it's 1, 0. 1, 0 is about, I'll use a different color, otherwise you won't be able to see it. I will use green so that it matches the rest of the green stuff we're doing here. There's 1, 0. There's the vector 1, 0. But where is the vector -4, 0? Where is that vector? It is back here. And although it's negative, it's just a scalar. So apart from the negative sign, we can say they're going in the same direction. Right? If we're talking about velocity, then this vector just shows negative velocity, where this one shows positive velocity. Right? So we're going in the same direction, and that is what an eigenvector does. It takes a matrix and uses multiplication by that matrix, or the multiplication of the matrix by the vector, to produce another vector in the same direction. That's kind of a graphical representation of what's going on here. So all we've talked about in this video so far is what is an eigenvector and what is an eigenvalue, and what does it mean graphically. So in the next video, we're going to talk about part of how you go about finding an eigenvalue. I've given you a couple of matrices, or I've given you a matrix here, and I've given you a couple of vectors to play with, right? We played with this one, which turned out not to be an eigenvector, and we played with these two, which turned out to be eigenvectors. But how do we find these if we don't know what they are? Well, that's not quite the subject of the next video. It's the one after that. But in the next video, we're going to talk about something called the characteristic equation, which helps us determine what the eigenvalues are.